Okay, with the preparations we provided in the previous videos, we are now ready to look at a concrete implementation of a data encryption algorithm. And this data encryption algorithm is referred to data encryption standard, DES, which was used in the mid-1970s to the late 1990s. Okay, so to the late 1990s and early 2000, until advanced encryption standard was adopted in early 2000. In early 2000s, I believe that was in 2003. Okay, so DES was published by the US National Bureau of Standards, NBS, in 1977. This was a concrete, DES is a concrete implementation of a data encryption scheme called the Feistel Cipher scheme, FCS, which was invented by Horst Feistel. It is a symmetrical encryption and decryption structures. It is used for it uses 4 basic operations: exclusive OR, permutations, substitutions, and circular shifts. So we talk about 5 groups of basic, we talk about 5 operations, basic operations earlier. So all but the finite field operations. But for finite field operations, we have 4 of them, right? So addition, subtraction, multiplications, and divisions. So it uses exclusive OR, permutations, substitutions, and circular shifts. It was widely used from mid-70s to early 2000s. So all the bank transactions was secure, was encrypted using DES. And it was replaced in 2003 by AES. Okay. So since DES is a concrete implementation of the Feistel Cipher scheme, so we are going to now we are going to explain what this Feistel Cipher scheme is. Once we have understanding of this scheme, then any implementation of its substitution function will give you a data encryption and decryption. Okay, so now let's look at this scheme, FCS. So FCS divides your plain text or your original input string into blocks such that each block is 2 L bits long. Okay, and as we mentioned, that all our data is a binary string such that its length is divisible by 8. Okay. So of course, the length is an even number. So we divide your input string M into blocks, okay, such that each block is is 2 times L bits long. Okay, so this L, depending on what implementation you are going to use, it could be like 32, 48, that kind of things. Okay, so if your string M for the last block, it doesn't have 2 L bits, then you can pad the last block when needed. Okay, so as we mentioned earlier, using ASCII code, we can use white space ASCII code for padding. And then we use only the exclusive OR and substitution operations in FCS. Okay, so exclusive OR and substitution. It generates AND subkeys, we also call it round keys, of a fixed length from the encryption key. The reason sometimes we use round keys, sometimes we use subkeys, is that for each round, some of the rounds may use more than one key, subkey, okay, for instance, at the beginning or at the end, but usually they are just, subkeys are round keys. So we denote these round keys by k sub 1 up to k sub n. So this means that there are n rounds in FCS. So depending on implementation, this n could be 16, could be 32, right? Could be other numbers depending on your implementation. Okay, so then FCS divides each block into 2 parts. Call it L, the left-hand side, 2 parts of equal length. The left-hand side is denoted by L. The right-hand side is denoted by R. To begin with, each block is L0 followed by R0. And then it performs a substitution function F on an n L-bit input string and a subkey to produce an n-bit output, an L-bit output. So that's what that substitution function F does. It only, for each round, it only operates on half of the bits, okay? So remember, this substitution itself may not form encryption, okay? And the other thing I would like you to keep in mind here is that any substitution will work for this Feistel cipher scheme. In other words, it is encryption and decryption, but of course, not all substitution function would work well. So you need to work out a good substitution function. But for Feistel cipher scheme to work, any substitution function F will do. Okay, so encryption and decryption each executes n rounds of the same sequence of operations. Okay, now let's look at these sequence of operations. So on the left-hand side is a mathematical notations of this encryption and decryption, and on the right-hand side is a diagram. So each block, now this M is a data block now, okay? So sometimes we use M to indicate it is the input string. Sometimes we use M to indicate it is a block from the input string. Okay, so we don't want to put a subscript there. M sub I, because if we do that, then we have to say L sub I0 and R sub I0. So that will be cumbersome. So I want to make this clear. So now so this encryption is straightforward. Remember, we have only two operations. One is the exclusive OR operation. The other one is the substitution function. Okay. So so now we have n rounds. Okay. So if you look at this, you can see that. Let's say the output of the first round of L0 R0 becomes L1 R1, right? Okay, so that's one indicates the output of, so I, okay, this is subscript I indicates this is the current input of, it is the input of the current round. Okay, so for Li, so it is just the right-hand side half of the previous input. So the input of the previous round. So there isn't anything changed, but this R sub I is changed by operating on the first half of the input in the previous round, and then exclusive OR F on the second half of the previous input, and with a subkey ki. Now remember, any function f will do. Okay, so you do this for n times, and you get L sub n and R sub n. So now you swap these two, and you get L sub n plus 1 and R sub n plus 1, and that is your cipher text. So now let's look at the diagram. On the left column of this diagram, so to begin with, okay, so this is your input block or plain text block. The left half is L0, the right half is R0. So according to this, the right half is to be the left half of the next round, okay? So that means this going down to the next round. And then the left half of this input will do, so you apply this function f on the right half using the subkey k1, and that is f of r0 k1, and exclusive OR L0, you'll get r sub 1. Okay, so that's what r sub 1 you are getting. Okay, so then you repeat this same set of operations for n times, and then you get the output. So this is r sub n, this L sub n, this is r sub n. So you swap them, and then you get your cipher text block. Okay, now let's look at the decryption. So you are using the same set of keys, subkeys, okay? But then what you do, you also use the same set of operations, exclusive OR and F for each round, but then you work your way from bottom up. In other words, from your ciphertext here. So this is your input, okay? So ciphertext is your input. So first, we are going to write the left half as L0 prime, the right half is R0 prime. So then you apply the same algorithm, But for this, you are applying the keys in the reverse order. So for the first round, you use Kn, but anything else is the same until you get down to L. So L sub n prime and R sub n prime, and then you swap them again, and that should give you the plain text. But at least now, for now, we were just saying that it gets you a output string, which is L sub n plus 1 L, followed by R sub n plus 1 prime. So this is L sub n plus 1 prime, followed by R sub n plus 1 prime. So we are going to see that it is identical to your plain text input L0 followed by R0. Okay, so that is a proof. So the proof is done by mathematical induction proof. So this is what we need to show. We are going to show that the decryption algorithms produce the output of the decryption algorithm is M. So which means that we want to show that L, or let's do this. That means we want to show L0 prime, R0 prime under this decryption algorithm produce L0, R0, or we want to show that L sub n plus 1 prime followed by R sub n plus 1 prime is equal to L0, R0. So then we'll prove this by mathematical induction. And these are the equalities we want to prove using mathematical induction. So for any I want to show that L sub I prime is equal to R sub n minus I. So then, so this means that when I is equal to n, then I know L sub n prime is equal to R0. Okay, so similarly here, I want to prove for any I, R sub I prime is equal to L sub n minus I. So for the basis, we're going to let I be 0. So that's L0 prime. So we know L0 prime is L sub n plus 1. So that's how we rename L sub n plus 1. We rename it to L0 prime. But we also know that L sub n plus 1 is equal to Rn. Right? So this is, remember, when we get down to this, we do a swap that becomes an L sub n plus 1. Similarly, R0 prime is equal to R sub n plus 1. Okay, so this is, and which is L sub n. So when I is equal to 0, both 1 and 2 are true. So now we make a hypothesis. We are going to assume that for I less than or equal to n, we have this equalities hold. Okay, so this is a standard way to do mathematical induction. So we assume that for any I less than or equal to n, L sub I minus 1 prime is equal to R sub n minus quote I minus 1. Likewise, we assume that for all I less than or equal to n, R sub I minus 1 prime is equal to L sub n minus quote I minus 1, parentheses I minus 1. So now we want to conduct an induction step. So first we look at, so from here, we are going to look at L sub I prime, which is by the decryption algorithm. So this so else I prime from the previous r sub I minus 1 prime. Okay, so for this, we know that by hypothesis, by hypothesis, we know it is equal to L sub n minus I plus 1. And then by the encryption algorithm, okay, so this is the encryption part, we know that R sub n minus I is the previous left-hand side. So this is the, I'm sorry, we know that, so this is the previous, so this L sub n minus I plus 1 is equal to the right-hand side of the previous round. So this is R sub n minus I. So induction hypothesis, I proves this is true. So 1 is true. All right, so now let's look at the R sub I prime. Okay, we want to prove this now. So then we, by the decryption algorithm, it is equal to L sub I minus 1 prime exclusive OR F of R sub I minus 1 prime, and use this round key, subkey, K sub n minus I plus 1. Okay, so we know, again, this L sub I minus 1 prime is equal to the right-hand side of the previous round. Sorry, we know that by the this is by the hypothesis, okay? So this is a hypothesis. L sub I minus 1 prime is equal to this, which is n minus I plus 1. So, okay, so it should be minus 1 here. Okay, so this is a typo, or you get rid of this parentheses. All right, and then exclusive OR. So we know R prime, R sub I minus 1 prime is equal to this. We'll put this in. Again, this should be minus, okay? And we use this same round key, okay? Okay, so then we know that from the encryption, there's a minus I. Remember, it should be minus 1. So that becomes n minus I without the parentheses here. So let me make it clear. So I'll make a correction here. Okay, so there is no parentheses. So just n minus I plus 1. Okay. Because of this. So my pointer disappears. Okay. Now I can see now, but I cannot. All right. Okay. I cannot. All right, so I need to move back. Okay, do it again. Sorry about this mess. All right. Okay. All right, now I'm coming back here. So, and also this would be no parentheses. Okay, so okay, so from here, so this R sub n minus I plus 1 is equal to the left part of the previous round, exclusive OR F, okay? And the previous second half, the second half of the input to the previous round, and this K sub n minus I plus 1. So that's what we get. So now these F and that F is the same. We know exclusive OR is just subtraction. So if it's the same, then it becomes 0. So 0 exclusive OR this is this. So hence the second part is, the second is true. So then when you let I be n, then you get your output. Okay, so that is the proof of this Feistel cipher scheme works. So it is encryption and decryption, even though the substitution function F it uses is not, doesn't have to be an encryption. It doesn't have to be invertible. And moreover, any implementation of F will work, okay? So now let's look at a concrete implementation of FCS, and that is Data Encryption Standard, DES. So first of all, it let L be 32 in the Feistel cipher scheme. So the block size of DES is 64 bits. And the encryption key is 56 bits, okay? But it is represented also as a 64-bit string. The only difference here is that some of the bits are not used to generate subkeys. Okay, so still 64. And then DES, the number of rounds uses, the number of rounds of DES is 16. So which means that we let n be 16 in the Feistel cipher scheme. So then we need 16 round subkeys or 16 round keys. So now we first look at the subkey generation algorithm. So it first removes the AI bit, okay, which means that it removes K sub 1, K sub 2. I'm sorry, it moves K sub 8, K sub 16, and K sub 64 from K. Okay, so then after you removing these bits, these 8 bits, you got 56 bits left. So these 56 bits are used to generate subkeys. And then it performs an initial permutation. So this is a permutation on the remaining 56 bits of K, and that initial permutation is denoted by IP, initial permutation, okay? And this is for key. So the input is the 64-bit key, 64-bit key. Okay, and then it splits this 56-bit key into 2 pieces. Each piece has 28 bits, okay? So U0 is the first half, B0 is the second half. So U0 has 28 bits, B0 also have 28 bits. And then it performs left circular shifts on U sub 0 and V sub 0 for a defined number of times. producing U sub I and V sub I. So this is how it is done. So this is a left circular shift. Z sub I means the number of times on a particular input I. So you can check the value of this Z of I from a table in your textbook. Now let me tell you where it is. This is on page 53. Okay, so there is a table somewhere in the middle that gives you that value. So either 1 times or 2 times. Okay, so I need to remove this. Okay. All right, and then after that, so at the end, okay, you get U sub 16 and V sub 16. So for each I here, you permute. So you permute the resulting. Okay. So for each I, you permute the resulting UI followed by VI using a defined complex permutation. Okay, so it was a 56-bit input, so you want to produce a 48-bit output as a substring. Okay, so this is a compression function. So the input here has 56 bits, and the output is 48 bits. So you need to compress a little using a predefined function, P sub key. Again, the actual definition. This, you can find it on page 56. And IP sub key is given on page 53 in your textbook. Okay, now I got K sub I. So each of these is your 48-bit sub keys, I from 1 to 16. Okay. So now let's look at the substitution function. Okay, so F, this is the substitution function in FCS. And the implementation in DES is the following. For the second half of the input to the previous round, that's R sub I minus 1, it applies a permutation. So if first, excuse me, so this EP is this EP is responsible for turning a 32-bit input. So now this is a 32-bit input into a 40-bit output because your key length is 48 bits. So this is expansion and permutation. Okay, so now after this operation, you have a 48-bit string, and then you apply a substitution, okay, S to So this, you first exclusive OR KI, right? And then you apply S. That will produce, now this is a 48 bits. By substitution, I want to compress this 48 bits into 32 bits. because the output of this function f should be a 32-bit long string. Okay, so that's what this S is for. And after that, you perform a permutation. Okay, so now let's look at what this substitution function S does. Now, the input is a 48-bit string. Okay, so it turns a 48-bit string Y. That Y is here. So Y is equal to EP of R sub I minus 1 exclusive OR K sub I. So that's Y. That's string Y. And then that's 48 bits. So you apply S to Y, you should get. Then we want it to produce a 32-bit string. Let's call it Z. And this S function uses 8 matrices. This is a specially designed matrices. These are specially designed matrices. And each of these matrices is 4 rows and 16 columns. And each matrix is called an S box. So you have 4 rows, 16 columns. So then now remember your input is 48-bit. So we are going to break Y into 8 blocks, each with 6 bits long. Okay, so then each block uses one S box because you have 8 X boxes. Okay, so then the entry in this S box is a 4-bit string. Okay, so now you have 8 blocks. So for each 8 blocks, the input has 6 bits, but after applying a S box, you get a 32-bit, you get a 4-bit string. So 4 by 8 is 32. So that's how you get a 32-bit output. So now for the, let's say the ice block, okay, you have a block. So let's say the ice block, we write that block 6 bits into B sub 1 up to B sub 6. Now, how do we apply it? So some of these 2 bits will be a row number, and some of the 4 bits will be a column number. In particular, in this case, we use the first bit and the last bit to be the row number, and the middle 4 bits to be the column number. So you do a table lookup, get the entry, and that will be the value of S on the ice block. Okay. So then you get a 32-bit output, and then you apply P. This is a permutation that still gives you 32-bit output. So that's what this substitution function does. So the key components here is these 8 specially defined matrices, which are designed to resist mathematical analysis attacks. Okay, so obviously you can think of there will be nonlinear effects here to make mathematical analysis attack hard to do. Okay, so that with this substitution function f defined in DES, now let's look at the encryption step. So DES encryption, okay, so this is your data block. We first apply an initial permutation on this data block M, and after that, so that will be, we'll start from L0, from this, okay? Actually, this initial permutation is defined on page 57, but it just the intention of this is to add one step of diffusion. Okay, so now we know that so L0 has 32 bits long, same is. So is R sub 0. So then we do it for 16 rounds. So this is exactly the same as in Feistel Cipher. But once you get down to your output, okay, so you do the initial, the inverse. So this is the inverse of the initial permutation. Now, permutation is 1-to-1 and onto mapping, so the inverse exists, and which is defined also on 57. Okay, so this is a pre-computed. Of course, when you write your code, these pre-computed things will be coded in your program. So that's it. So this is the encryption step. Decryption will be the same, but you just follow the Feistel Cipher scheme. Okay. So you get a concrete implementation of Feistel Cipher scheme, and so we have DES. So the question is then, is DES good enough? That means we're going to look at the security strengths of DES. So the strengths of it relies on, of course, we know the number of rounds, the length of this secret key, and the construction of the substitution function. It turns out that the number of rounds and the construction of the substitution functions are very strong, but unfortunately, the key length is not strong enough. Okay, so brute force attack can be used. Okay, so, but nevertheless, DES was used up to the 1990s, okay, late 1990, and when problems were identified, and before AES came into place, and there was an intermediate remedies for making DES stronger by applying several DES together. So we're going to mention that in the next video. So then people began to take on the DES challenges. Okay, so in order to find out how strong DES is, there are there are DES challenges posted. There were DES challenges posted with the input and also output and invite. And people were invited to crack, to take on these challenges and try to crack DES. So as we said that the key length, the actual key length is 56 bits, okay? So altogether, you have this many possible keys. So brute force, okay, actually, the brute force attack was applied by building, so people build special purpose of computers to brute force attack DES. And then in the 1997, okay, so there was a program that could be run on all idle machines, right? To crack some of the, to try some of the keys, okay? So because the brute force attack, you try all keys. So then in 1997, on the internet, it took only a few months to crack DES, okay? And then this technology was improved with a dedicated special purpose computer. And it was done in a few days. And after all, then in 1999, okay, by combining these methods, and it only took 22 hours to crack DES. Then obviously, 22 hours. So you only take 22 hours to crack DES encryption. So this is not secure at all. So then what do we do next? Okay, so we start over. And of course, now we have AES, but before AES, so after finding, so in 1999, after this DES was found, vulnerable to the brute force attack. So then people needed a intermediate solution before a new standard was devised. Okay, so that will be the topic for next video.